Hello and welcome. In this particular video I would like to take the rather cryptic looking Biot Savart Law, named after two Frenchmen, and try to make it a little less mysterious by showing how it's used and then doing a couple of examples where we actually apply the Biot Savart Law to calculate the strength and also the direction of a magnetic field that is produced by a moving charge. So let's first look at some examples of when we would use the Biot Savart Law. Well, on this page I've got 5 different examples showing when we might use the Biot Savart Law and the question we would answer with it. In each case we have some moving charge, and we could ask, if we locate some point P around that moving charge, how strong is the B field going to be at that point, and what direction would it point? So here in the upper left we have a rightward moving positive charge, and we've got a whole bunch of points around it. This one here that I'll circle in purple, that one I've labeled P, and we could say, well, how strong is the field at that particular point? There's many other points. In fact, here's one here that isn't labeled, but we could demonstrate why the B field at that particular spot would be 0, but not at the point down below it here or the point above it. Over here on the right, we've got just a length of wire that I drew in green, and we could say, well, how strong is the field out at this location? And that's a little tougher to answer, and this is a case where Biot Savart Law is a little bit not practical, but we could say, well, what about the small little part of the wire that I marked in red there? Could we describe how strong that part of the wire is in terms of the field that it creates at point P? And then down in the bottom we've got a couple of loops of wire. Now those are still moving charges, but what we have here are actually complete loops where we might have current flowing around them. And if we put a point P here at the very center of the loop, or even move that point P off the actual plane of the loop but still on the center axis, we could say how strong is the field at those points. And then in our last example in the bottom right, we've got a little length of wire. We'd say, okay, if we go above the wire a little distance, how strong is the magnetic field there due to that little length of wire with current going through it? So there's a few examples. Now let's just take one here and make it a little more practical and show you the nuts and bolts of using the Biot Savart Law. Here on this page I'm going to show 2 different examples of how the Biot Savart Law can be used. And the 2 examples actually are presented in 2 different forms for the equation. So the upper form is what we're going to use when we have a point charge such as this. I have a positive little charge here marked as a Q. And the bottom form is if we have a whole bunch of charges moving through a wire, in the case like we have here, and we show it as a current I. So let's just take a look at the upper example first and account for all the different values that are involved in the calculation. We first have the fundamental constant that we use for magnetic fields. That's known as the permeability constant, and we use mu naught. I apologize for using mu in yet another different way, but that's just the form that the convention uses. And mu naught has a value of approximately 1.26 times 10 to the minus 7. You can find that value in your textbook, and it's often used over 4 pi as it is here. And then we have Q, which is the actual charge that's moving, that's creating the field. We have V, which is the velocity vector associated with that moving charge. And we have an R vector that shows up in 2 different ways. In the upper part, that's just the unit vector, so it doesn't have any magnitude. I guess you could consider it a magnitude of 1. We only need it there so that we can use the direction in a cross product operation when we're finding the direction of the B field. We use it in the denominator just as a magnitude, and it's squared just as the Coulomb's law is squared. So in this example here, if I'm interested in knowing the strength of the field up there at that point P, then R is the vector that goes from the location of the charge up to the location where I want to know the strength of the field. So I'll just represent that here in green. So that's my R vector. Its direction goes here, and its magnitude goes down here as a square. One thing that they render nicely on this diagram that I borrowed is that the field is relatively weak out here, and that's for two reasons. You're relatively far away from the charge, and you have less perpendicularity between the v vector and the r vector. But when you look here, this point is relatively close. If we mark it right there, relatively close to the charge, and the r vector associated with that, which I'll draw in green here, is completely perpendicular to v. And remember, the property of the cross product says that when you're completely perpendicular is when the cross product is the biggest. Now take a look at these special points out here. Why would b equal to 0 there? It's not because there's not a q or a v or an r associated with those. It's because there's absolutely no perpendicularity between an r vector. Let me draw an r vector here if it can not be too confusing. That would be the r vector for that point. Notice it's completely parallel to the velocity vector. So an important property of the magnetic field associated with a moving charge is that there is no field right along the line of the motion itself. Now if we take a look at the bottom example, we have a wire that I've redrawn in green there, kind of a bent into an L shape. And we might ask, well, what is the strength of the field out here at this point? And I've written the equation a little differently. First, in place of Q and V, I replaced it with IDS. Now that can be very confusing, but IDS is what's indicated here by this little red length. The I is the actual current in the wire, and DS represents a short little segment of that wire. We have to do it that way because every little segment of this green wire is creating a different strength field at that point P. So we just have to find each individual one and then add them all together. So that's why we're using a dB to describe just the small contribution of that little red length of wire at point P. And then we would do a summation, or actually probably more likely an integral, to do the superposition and sum up the effect of the entire length of wire. I think everything else is pretty much the same here. You got the r vector from that location of the moving charge out to point P, and that shows up both as a unit vector here and as a magnitude down there, and here's our mu naught over 4 pi. So really, other than the IDS replacing the QV, there's not a whole lot different about using that form. And in fact, this bottom form is used much more commonly than the upper form. On the next screen, I'm going to talk about how we use the right-hand rule to figure out the direction of the field created by a moving charge. I think it's going to be a little easier to see on a new page. Now I'm going to make an attempt to describe the direction aspect of the Biot Savart Law, which is admittedly difficult to do on a two-dimensional screen, so it's something we'll work on more in the classroom. Let's just take this spot up here at point P and try to describe what we know about the direction of the B field vector there and how they figured out which way it points. Remember that the direction of the B vector is found by crossing a V vector by the R vector. So we have to imagine ourselves located at point P, and we say, okay, first, what is the direction of the velocity vector? Well, on this figure, it's pointed pretty much rightward. So we'll call that V. And what is the direction of the R vector? Well, that's kind of up, angled up and to the right. Doesn't really matter how long you draw these because we're not looking for any magnitude, we're just looking for direction. So there's our R vector. Now, what you have to imagine is taking your right-handed fingers and turning them so that V is rotating towards R, as I've indicated there by that little arrow. And as you spin your fingers that way, your right-handed thumb should naturally point towards you. Now it's very difficult to draw something pointed towards you, but maybe you remember the convention for this. And that is, for a vector coming out towards you, you actually put a little dot And that is the direction that the b vector points. And if you notice, that's exactly the b vector that they've indicated there. Now for the bottom figure, we have an I crossed into an R. So here's the vector first that we're crossing. It's the I ds. And I'm going to mark this in red. So what direction is that? If we're out here at point P, we say what direction is the current going? As we look at it, it's going, I guess, somewhat up, maybe a hair to the right. So I'll draw it something like that. So that's the direction of the I ds vector. Really, the direction part belongs to the S, but it's just the direction of the current at that location. And what is the direction of the R vector? Well, you can see there that they've got that marked in a little bit up and mostly to the right. So now we have to imagine, how do we rotate the ds vector towards the R vector? That's what I would describe as a clockwise spin. So now if you spin your right-handed fingers clockwise, it should make your thumb point in the opposite direction, which is going into the screen or away from you. And so we indicate that by a little X. And that is the direction of our b vector in the second case. Well, now I'll show you a good practical case of where we can use the Biot Savart law. It's if you were asked to find the B field at the center of a current carrying loop. Now don't bother to ask how we could have a current carrying loop when you don't see any batteries or wires connecting it to anything. We just don't ask questions like that in physics. We're just going to say how strong is the B field due to that. And I'm going to use the form of the Biot Savart law that I used before with the current. And we start with just an expression for a small contribution of a piece of that loop. And so it looks like this. It's the fundamental constant mu naught over 4 pi I ds. That's the vector that just represents a little length of that loop, crossed with the R vector all over the magnitude of that R vector squared. Now if you're new to the calculus thing, you might be a little nervous going into this because in order to get to the entire magnetic field created by the entire loop, we are going to need to do the sum of all of those little contributions. But we're going to find out this is actually a relatively trivial integral to do, and I'll show you why. Remember that anything that is not different in an integral can be taken out of the integral and put out in front. Things that are just constant, not really variable. And what things are those? Well, certainly our fundamental constants. And the current is the same through every little segment of that, so we can take that out. And here's something that you don't find except for a case like this and similar cases where all of the currents, the little segments of current, are the same distance away from the center of the loop. This would not be the case if we were anywhere but at the center of the loop. So this r squared is really not a variable, but it's just the radius of the loop itself from each little piece of current to the center of the loop. And we're not really going to have to worry about crossing anything either, because the right-hand rule will show you that we get the same direction every time we cross a little segment of current with its r vector, no matter where we are on that loop. Now we do have to take into account a magnitude factor for the cross product. Anytime you have a cross product, you incorporate the sign of the angle in between the two vectors. So in this case, it's between the ds vector and the r vector. But if we just use an example here, perhaps on the rightmost side of our loop, we've got an I vector, or a ds vector, that's pointed up, and we've got an r vector that's pointed inward. Those are completely perpendicular. And that's true no matter where we are on the loop. So that means we don't even have to account for the cross product. So a whole lot of things are simplifying for us here. And let me show you what we get when we pull all those things out of the integral, get rid of the cross product. I think you're going to be surprised. So here I've rewritten everything and taken all that stuff out that I said wasn't really a variable. I also introduced here a value of capital R, that's in particular the radius of this circle. That's a little different than the small r, which just generically describes how far the point in question here is from each little segment of current. Those just happen to be the same, little r and big R, in this problem. So everything came out, except of course we can't take the ds out. That's our variable and we kind of have to maintain that. So we're just taking the sum of all the little ds's, all the little segments of current. Well, if you go around the entire loop, what are you going to add up there? You're going to add up the entire circumference of that circle. So now we can rewrite this without the integral sign, and everything stays the same out here, and we're just going to get the circumference of that circle, which is 2 pi r. And a couple things nicely cancel here. We have a pi up and down, we have an r on the top, we have a couple on the bottom. We could cancel out the 2 with part of the 4. And when all is said and done, do a little simplifying. Here's what we get at the center of a loop of wire. We get mu naught I over 2 r. And the direction of that, as shown here, is, I guess we'll call it coming out towards you. And that can be found by the right-hand rule, crossing each little ds vector with the r vector that goes with it. And every time you do that on every little part of the loop, you get your thumb pointed directly out towards you. So that's a nice expression. Not one I want you to memorize, but one I want you to be able to be comfortable using Biot and Savart. And really, that's probably the only case where you're going to have a situation to apply the Biot Savart law to. So if you need to see that again, by all means, you can play that back again, and we can clarify things in the classroom when we're together again. So hopefully that's enough to get you a good start on any Biot Savart kinds of problems, and we'll just see you in the classroom.